So in the previous video, we reviewed how to graphically look at whether a function was increasing or decreasing, which is how we did it in pre-calculus. Now we want to develop the concepts that are needed to use calculus to determine if a function is decreasing or increasing. So here's the idea. I'm going to do two slides where we try to do kind of a conceptual development of using calculus to determine intervals over which we're increasing, decreasing, or constant. So here's my function g of x. It's the function in black. And g prime of x, the derivative of x, is here in a tannish color. And what I want to recognize is that my function g of x is increasing up until the point right here where the tangent line is equal to 0. And when the tangent line is equal to 0, we know that g prime, the derivative, is equal to 0 because the derivative gives us the slope of the tangent lines. And then I want to look at the function and see that it's decreasing now that I've gotten past x equals 0. Now it's decreasing. And it looks like at x equal to 1, we have a tangent line of 0 again. And this would be where g prime was equal to 0. And then the function begins to increase and increases forever after that point. So the first thing to notice is that the derivative being equal to 0, at x equals 0 and x equals 1 is actually establishing the break between the function being increasing and decreasing, or decreasing and increasing. So the derivative equal to 0 establishes the break between the increasing and decreasing function. And remember that when the derivative is equal to 0, the x value that gives us a derivative equal to 0 is what we call a critical number. So we've already looked at calculating critical numbers. And critical numbers were either places where the derivative was equal to 0 or undefined. So if we want to find intervals over which the function's increasing or decreasing, step one is to find critical numbers. And then you use those critical numbers to set up test intervals. So I'm going to run from, on the x-axis, from negative infinity all the way up to 0, because at x equals 0, the derivative is equal to 0, and that gives me that break between increasing and decreasing function. And then between here where I have a derivative of 0 and here where I have a derivative of 0, the function's decreasing. So look at the interval, the open interval over which the function is going down or decreasing, and recognize that that's happening at critical numbers, that these are critical numbers of the function g of x, places where the derivative is equal to 0. And then once we step over this derivative of 0 right here, we see the function's increasing. So it's increasing from 1 to infinity. So step one, if you want to use calculus to determine intervals over which a function's increasing or decreasing, is to find the critical numbers and use the critical numbers to establish open intervals. That's step one. And we could do this without looking at the graph. We know that finding the critical numbers is simply a matter of setting the derivative equal to 0 and solving for the input values that generate a derivative of 0. The next thing that you want to notice is that when the function is increasing, if we look at the slopes of the tangent lines to the graph, we want to notice that we have positive tangent lines when the function's increasing. And this makes sense. The derivative, which describes the slope of the tangent lines, tells us the rate of change of the function. So if the function is increasing, the derivative needs to be positive. The tangent line slopes need to be positive. So when you look at the derivative of the function, all through here the tangent lines are positive, and we see that the derivative, g prime, is positive up until we get to this critical point. So step two is look at f, well, my function's g, look at the derivative, look at g prime, and determine is it positive or negative. Look at g prime. What is the sign of g prime. If g prime is positive, then the function's increasing because the rate of change of the function is positive. So the interval from negative infinity to 0 is going to be an increasing interval, because when we look at the derivative in this interval, we see that the derivative is positive. And if the derivative is positive, the rate of change of the function is positive, the function must be increasing. When we step to the second interval, what we want to notice is that where the function's decreasing, if we draw in a tangent line any place where we want, the slope of that tangent line is negative. So in fact, because the function's decreasing, we can see that the derivative over the interval from 0 to 1 is actually always negative, corresponding to a decreasing function. So because the derivative is less than 0, the function is decreasing. And then once we get past this critical point here at x equal to 1, notice if we draw on a tangent line any place that we want, the slope of that tangent line is positive. That tells us that once we get past this critical point, this critical number, look at the derivative. Once we get past here, the derivative is positive, which is why we have an increasing function, because the derivative's positive, so increasing. So if you kind of summarize this, if you're trying to identify intervals over which the function's increasing or decreasing, you want to find the critical numbers, establish open intervals using the critical numbers, the places where the derivative is equal to 0. In the next slide, we'll see places where the derivative might be undefined also gives us critical numbers. But use the critical numbers to identify open intervals, and then calculate the derivative and ask yourself, is the derivative positive? Is the rate of change positive? If it is, the function's increasing. Is the rate of change or the derivative negative? Then the function is decreasing. So next example, here's a simple absolute value function. See, here is the location of the critical number. We'll call this A. So x equal A is the critical number. That's the place where the function, we'll call him f of x, is undefined, right? We have a cusp in the graph. So the derivative is not the function, but the derivative of the function's undefined at that cusp. But notice here the function's decreasing. Here's the critical number. We'll say that's happening at A. So the open intervals would be run from negative infinity on the x-axis up to where the derivative is undefined, because that's the location of a critical number. And then go from that critical number, the function's going to infinity with respect to the x-axis, establish your second open interval. Here I can see that the function's decreasing, but notice we could use the derivative to determine that. Here's the derivative of the function over the interval from negative infinity to a, and we can see that the derivative is negative. It's below the x-axis. So we can conclude that the function f of x is decreasing over this open interval because the derivative is negative. The rate of change of the function is negative, which means the function outputs are decreasing. Once I step over this critical number at x equal a, where the derivative is undefined, I see that my function is increasing. But notice we could use the derivative of the function to determine that. Here's the derivative starting at the critical number where the derivative's undefined. Here's the derivative. It's really an open circle there. The derivative's always positive because the derivative or rate of change of the function is positive. The function is increasing. So to summarize, and then in the next video we'll show examples of using this summary. Hey, if you have a continuous function over an open interval, if you want to find open intervals over which your function is increasing or decreasing, go through the following steps. Find the critical numbers. Find the critical numbers. Determine where the derivative is equal to 0, or where the derivative is is undefined, because the places where the derivative is undefined or 0 will be places where the function may change from increasing to decreasing. So find those locations where the function may change from an increasing to decreasing function or vice versa. Establish open intervals using those critical numbers. Then look at the derivative. On each of the open intervals you find, determine whether the derivative is positive or negative. If the derivative is positive on an open interval, the function f of x is increasing. If the derivative of a function is negative, then the function itself is decreasing. So we use those sign changes of the derivative to determine whether our function is an increasing or decreasing function on a given interval.